Imagine two pots of tomatoes, same seeds, same garden, same summer heat. The first pot sits under a careful gardener, someone who wakes every morning at 6, drags a hose across the yard, and waters for 20 minutes. By midday, the top of the soil is already bone dry again. The leaves curl inward slightly. The roots, sensing stress, pull back from the surface. The plant survives, but it is always fighting. 3 meters away, the second plant is different. No one waters it. Not today, not yesterday. But when you press 2 fingers into the soil near its base, the earth feels cool, firm, and quietly moist, even at noon, even in the middle of August. Between the roots of the second plant, buried just below the surface, is a plain clay pot. It costs less than a cup of coffee. It has no pump, no timer, no battery, no screen, and yet it delivers water at a rate the roots themselves control. What if the most intelligent irrigation system ever built is not a product, but a simple piece of fired earth that humans buried in desert gardens over 4,000 years ago? Most gardeners believe water is the simple part. You apply it, plants absorb it, job done. But this belief misses the most important variable in the entire system. Not how much water you give, but when the roots can actually use it and at what pressure it arrives. Here is what actually happens when you surface water a garden. You apply water at the top of the soil. Gravity pulls it down through the fastest paths, usually existing cracks, air gaps, loose organic matter. A significant portion of that water evaporates within the first 2 to 4 hours, especially on hot days. Studies measuring soil evaporation under direct sun in warm climates show surface moisture losses ranging from 30 to 60% within a single afternoon. The water that does penetrate distributes unevenly. The upper 5 to 10 centimeters may be saturated, while 15 centimeters below, in the active root zone, the soil remains dry. Now the root faces a problem. It senses moisture above it, but the signals from the surrounding soil, osmotic pressure, soil matrix potential, tell it the available water is unstable. The plant responds by partially closing its stomata. Photosynthesis slows, growth slows. The plant is technically watered, but biologically stressed. This is the hidden variable, soil matrix potential. It is the measurement of how tightly water is held by soil particles, expressed in kilopascals. A well-hydrated root zone maintains a matrix potential between 10 and 30 kPa. Beyond 70 kPa, most vegetable crops begin showing measurable stress responses. Beyond 150 kPa, growth effectively stops. The problem with surface irrigation is not the volume of water. It is the instability. The root zone cycles between saturation and stress repeatedly throughout the day and week. Each cycle costs the plant energy, energy that could otherwise go toward growth, fruit development, and root expansion. The solution is not more water. The solution is continuous, stable, low-pressure delivery directly in the root zone. Delivery that bypasses evaporation almost entirely. Delivery that responds to soil demand rather than a human schedule. The hidden variable is not water volume. It is consistency of supply at the point of use. The global drip irrigation market is currently valued at over $6 billion US, with projections pointing toward $10 billion by the end of this decade. This market sells a specific promise: precision water delivery directly to the root zone, reducing waste and improving yield. The promise is real. Drip irrigation does work. But let us look at the actual cost structure for a home gardener. A basic drip irrigation kit for a 20 square meter vegetable bed typically costs between $80 and $200, depending on brand and complexity. Advanced systems with pressure regulators, timers, and soil moisture sensors range from $300 to $600 for the same area. Installation requires careful planning of emitter spacing, mainline routing, and water pressure calibration. Most systems also require annual maintenance, replacing emitters that clog with mineral deposits, replacing tubing that degrades under UV exposure, and recalibrating timers seasonally. The dependency cycle is quiet but real. Once installed, the system requires electricity for timers, compatible replacement parts from the same manufacturer, and technical knowledge to troubleshoot when a zone fails. The gardener no longer reads the soil, they read the screen. Now consider the alternative. An unglazed clay pot, the size used in Olla irrigation, costs between $2 and $5 USD in most markets. In regions where pottery is locally produced, it may cost less. You bury it. You fill it with water. You walk away. That is the entire system. No tubing, no emitters, no timer, no electricity, no manufacturer dependency, no annual maintenance cost beyond occasionally clearing the pot neck of debris. One Olla pot can serve a root zone of approximately 50 to 100 centimeters in radius. A standard vegetable bed of 20 square meters can be served by 4 to 6 pots. Total material cost, under $25. A system that costs 10 to 24 times less, requires no electricity, and has demonstrated efficacy across 4 millennia of agricultural history. This is not an argument against modern irrigation. It is an argument for understanding which tool a particular situation actually requires. The Olla is not a new idea. It is not a gardening trend. It is one of the oldest documented irrigation technologies in human history. Archaeological evidence places clay pot irrigation in northern China as early as 2000 BCE, during periods when the Yellow River Plain required water management across dry season agriculture. The technique appears independently in pre-Columbian cultures of the Americas, in ancient Persia, and across North Africa, particularly in areas bordering the Sahara, where water conservation was not a preference but a survival requirement. The mechanism was not invented by engineers. It was observed. Early farmers noticed that unglazed clay vessels buried near plants and filled with water caused nearby crops to remain visibly healthier during dry periods. The physics were not understood in formal terms, but the result was documented across generations of agricultural practice. In the 1930s and 1940s, American agricultural researchers revisited the concept. Studies conducted in arid regions of California and the American Southwest documented that Olla irrigated plots showed comparable or superior yields to surface irrigated controls, with water usage reductions between 30 and 70%. The technique faded not because it failed, but because it did not scale. Industrial agriculture in the post-WW2 era required systems that could be mechanized, automated, and deployed across thousands of hectares simultaneously. A clay pot in the ground could not be automated. It could not be branded. It could not be sold as a quarterly consumable. It was not replaced by something better. It was replaced by something more profitable. Research in the late 20th and early 21st centuries has formally revisited Olla irrigation. A 2010 study published in Agricultural Water Management found that subsurface clay pot irrigation reduced water use by up to 70% compared to surface drip methods in some vegetable crops, while maintaining equivalent or higher yields. The mechanism, once understood through modern soil science, is elegant in its simplicity. To understand why an Olla works, you need to understand 2 physical phenomena that interact at the surface of unglazed ceramic: capillary action and suction-driven seepage. Unglazed terracotta is not solid. Under a microscope, the wall of a fired clay pot is a network of microscopic pores. Channels left by the burnout of organic particles in the clay during firing and by the irregular packing of mineral particles. The average pore diameter in standard terracotta ranges from 0.1 to 50 micrometers, depending on firing temperature and clay composition. When water fills the interior of the pot, it encounters these pores and begins to migrate through them by capillary pressure. Capillary action is the tendency of water to move through narrow spaces against the direction of gravity, driven by the adhesive force between water molecules and the pore walls. The smaller the pore, the stronger the capillary pull. Now here's the elegant part. The rate at which water moves through those pores is not constant. It is regulated by the soil on the outside of the pot. When the surrounding soil is dry, its matrix potential is strongly negative. It is under significant suction. The suction gradient between the dry exterior soil and the water-filled interior creates a pressure differential that pulls water through the pot wall. The drier the soil, the faster the flow. As soil moisture increases and approaches the pot wall, the pressure differential narrows and seepage slows automatically. The system is self-regulating. The plant does not receive water on a human schedule. It receives water at the rate the surrounding soil demands. This is a passive, closed-loop feedback system. No sensors, no electronics, no algorithm, just physics. This passive regulation maintains soil matrix potential in the range of 10 to 40 kPa around the pot, the optimal range for most vegetable crops. Roots growing toward the constant moisture source develop a dense exploratory architecture near the pot surface. Root density in the active zone around Ollas is measurably higher than in surface irrigated controls. In some studies, 20 to 40% greater root mass in the top 30 centimeters of soil. This matters because root surface area is directly correlated with nutrient uptake efficiency. More root surface area means more contact with soil mineral exchange sites, more fungal hyphal connections in mycorrhizal networks, and greater overall metabolic capacity of the plant. There is also a thermal benefit. Water inside the buried pot is insulated from surface temperature fluctuations. During a hot afternoon, surface soil temperatures can exceed 40 degrees Celsius, a temperature at which surface-applied water evaporates rapidly and roots in the upper horizon experience heat stress. Water held in a buried clay pot remains within 3 to 5 degrees Celsius of the ambient deep soil temperature, typically 18 to 24 degrees in summer, delivering moisture at a temperature the root zone tolerates without stress. The combination of passive pressure regulation, optimal matrix potential maintenance, root zone thermal stability, and enhanced root architecture explains why Olla irrigated plots consistently show 20 to 50% improvement in water use efficiency compared to surface drip systems, with no reduction in yield performance across multiple crop types studied in arid and semi-arid conditions. Materials list. Total cost, $3 to $20 depending on scale. Unglazed terracotta pot, 15 to 30 centimeter height, 10 to 20 centimeter diameter, $2 to $5 per pot. Unglazed terracotta saucer or flat stone for lid, $1 to $2 food-safe beeswax or paraffin wax to seal the drainage hole, garden trowel, or spade. Why unglazed is critical. Glazed ceramic has its pores sealed with glass. Water cannot migrate through it. Any glazed pot, regardless of shape or size, will not function as an Olla. The seepage mechanism depends entirely on the open pore structure of unglazed terracotta. This is non-negotiable. Step 1. Seal the drainage hole. Most standard terracotta pots have a drainage hole at the base. This hole is too large and will cause rapid, unregulated water loss directly into the soil rather than slow seepage through the walls. Seal it completely using melted beeswax or paraffin, pushed firmly into the hole and allowed to cure. Alternatively, a smooth, flat stone placed firmly over the hole before burial works adequately. Step 2. Burial positioning. Dig a hole beside your plant, but not between the root ball and the surface. Position the Olla 8 to 12 centimeters from the main stem of an established plant and 15 to 20 centimeters from the stem of seedlings to avoid disturbing new root growth. Depth. Bury the pot so that 90% of its body is below the soil surface, with only the neck and 2 to 3 centimeters of the rim exposed above ground. This exposure is your access point for refilling. Step 3. Filling and sealing the lid. Fill the pot completely with water. Place the saucer or stone lid loosely over the opening. This lid reduces surface evaporation from the open neck, which would otherwise represent 15 to 30% of total water loss, and prevents mosquito breeding in standing water at the neck. Step 4. Spacing for multiple pots. One Olla pot with a 15 centimeter diameter and 22 centimeter height holds approximately 2 to 3 liters of water and effectively irrigates a soil radius of 40 to 80 centimeters, depending on soil type and ambient temperature. For sandy soils, place pots every 80 centimeters. For clay-heavy soils, every 100 to 120 centimeters is sufficient. A standard 4-meter vegetable row typically requires 4 to 5 pots. Step 5. Refilling schedule. In hot, dry conditions, a single pot will empty in 2 to 5 days. In cooler or more humid conditions, one filling may last 7 to 10 days. Check the water level every 2 to 3 days initially to understand your specific soil and climate conditions, then adjust frequency accordingly. The Olla system is not universal, and it is important to understand where it underperforms before committing to it for critical crops. First, soil type determines effectiveness significantly. In very sandy soils with low water retention capacity, the seepage radius is narrow and dissipates quickly. Sandy soils dry fast near the pot's surface, which actually increases flow rate, but the water does not remain available long enough to maintain consistent moisture between the pot and the root tips further away. In these soils, supplemental surface mulching is required. Second, Ollas are not designed for seedling germination. The seepage zone is subsurface. A germinating seed needs consistent moisture at the very top 1 to 2 centimeters of soil, a depth the buried pot does not reach adequately. Maintain surface watering during germination and early seedling stages. Transition to Olla primary irrigation once the seedling root has reached 5 to 8 centimeters depth. Third, in waterlogged or heavy clay soils with poor drainage, the external seepage pressure differential is reduced or absent. Ollas rely on soil suction to draw water out. If the surrounding soil is already saturated, seepage stops, which is actually a feature, not a fault. But it means Ollas provide little value in already wet soils. Fourth, scale. An Olla pot holds 2 to 4 liters. For large commercial plots, this requires significant labor for refilling. This is a technique suited for home gardens, small intensive beds, and community plots, not for hectare-scale operations. The best time to install Ollas is at the beginning of the planting season, before transplanting seedlings, or shortly after transplanting when plants are still in their establishment phase. Installing them at this stage allows roots to develop their architecture from the beginning in response to the consistent moisture source. If installing beside established plants, those already with root systems 10 or more centimeters in depth, the Olla still works effectively, but allows 7 to 14 days for roots near the pot to begin responding to the moisture gradient before evaluating results. Week 1 to 2, establishment phase. Soil around the pot will absorb water as the system equilibrates with surrounding soil conditions. The pot may empty more quickly in the first few days as dry soil draws water aggressively. This is normal. Refill is needed. Week 2 to 4, active growth response. You will begin to notice changes in plant posture and leaf texture. Leaves on Olla irrigated plants typically show less midday wilting, firmer leaf texture in early afternoon, and slightly darker green coloration in the foliage nearest the Olla side of the plant. These are signs the root zone is maintaining consistent hydration. Week 4 onward, refill rhythm stabilizes. By week 4, you will have a clear pattern of how often your specific combination of soil, temperature, and plant size requires refilling. Most established vegetable crops in warm summer conditions require a refill every 3 to 6 days per pot. In peak heat, every 2 to 3 days. Visual signals of success. Run your fingers through the soil 10 to 15 centimeters from the pot wall at a depth of 5 to 8 centimeters. In a functioning Olla system, this zone should feel consistently cool and just moist. Not wet, not dry. When you eventually transplant or turn the bed over, you will find a visible network of fine root hairs concentrated around the pot wall. This is the direct evidence of the plant's response. Visual signals of failure. Soil immediately beside the pot wall is waterlogged while the rest of the bed remains dry. This indicates the base hole is not properly sealed, releasing water too fast through the bottom rather than slowly through the wall pores. Reseal and retest. There is a version of modern gardening that is entirely transactional. You buy a product. The product provides a service. When the product breaks or becomes obsolete, you buy its replacement. You never need to understand what is happening underground, in the soil between the root hair and the water molecule. The system handles it. You stay dependent. The industry stays profitable. And then there is another version. In this version, you understand that unglazed clay has pores, that pores create capillary pressure, that capillary pressure responds to soil suction, that soil suction is determined by how much water the root has already consumed, that the root, by consuming water, is signaling for more, and the pot, by the laws of physics, is listening. No electricity required, no quarterly filter replacement, no app notification telling you your garden is thirsty. This is not nostalgia. It is not primitivism. It is the recognition that biological and physical systems, when understood correctly, are often more elegant and more efficient than engineered substitutes. The Olla is not competing with modern irrigation. It is offering something modern irrigation cannot: a passive, self-regulating system that responds to the plant's actual physiological demand, not to a pre-programmed timer. The 4,000-year survival of this technique across dozens of independent cultures and climates is not coincidence. It is evidence. The knowledge was not lost, it was made inconvenient. In the next video, we go underground with something even simpler, a method using raw biochar and a $2 bag of agricultural inoculant that permanently restructures the water-holding architecture of your soil, reducing irrigation need by up to 40% over a single growing season. A technique tested in sub-Saharan Africa and quietly adopted by university research plots worldwide. But that is for next time. For now, bury the clay. Fill it with water, walk away. You just need to understand the invisible layer.